Awesome. Okay. So today's lab agenda is to look at some key linear algebra skills, and then also the linear algebra for quantum gates. If we have time, we can go through a QxQ review, kind of part 2 to continue keeping those skills fresh, let's say. And even if we don't, it's not a bad idea to go through the solutions themselves. Okay. So the learning objectives for today. So the main things that I'd like you to focus on is to focus on the skills of finding the norm of vectors. I know we just talked about that last week, but it can be a difficult skill. And so try your best to focus on it. See if you can kind of start to have it click now. Also focus on multiplying matrices with vectors and matrices with other matrices. So this is a newer skill, but it will be an important one and is part of kind of the bigger and bigger stuff that we're building up, as well as using math to apply gates to single qubit quantum states. Now that last bit may sound particularly fancy, and I would argue it is pretty fancy and cool, but actually it just comes down to this basic idea of multiplying matrices and vectors. So I would argue really your goal today is to focus on norms of vectors and multiplying matrices with vectors or other matrices. I would say it's those two main goals, and you then will be able to see how to do this last one, to apply gates to a single qubit quantum states using math. And if we get to the QxQ part, this is what we will go through. Okay, this is the attendance code again, but I've shared it in the chat, so if anyone doesn't have it, then do let me know. Okay. All right. So today's lab is going to be primarily math practice, right? We did that last week. We will likely continue in the future. And I know that that can be a little tiring sometimes. For some people, it can be a little scary. So I really just want to emphasize that this is really just like athlete training for strength and muscular endurance, but more for your mind. So it's math skills that will only become muscle memory if you practice. So it's all about practicing this so that at some point, it's not nearly as hard because you're just used to doing it, right? You've built up the muscle memory, you've built up how to do it, and you in fact won't need to think through it as much. So I promise you that the more you work on this, the more it will become clear. But right now, there's going to be a lot of parts that may not be clear, that may be hard or uncomfortable. Particularly if you're not that into math or you don't feel that way. But hopefully as you go throughout, you can really just focus not on the task of fully understanding it, right? Really what I'm trying to say is don't focus on trying to fully understand everything we talk about. That is not the goal today, or even for the foreseeable future. The goal is to get some training, to get some strength training and some endurance training here. Right? To just build these muscles up a little bit more, get a little more practice. And we'll just kind of keep doing this, right? You don't exercise once in your life and then you're good and fit for the rest of your life. You need to keep coming back and doing it. That's exactly the same here. So as just like last week, it will be good for you to have paper and a writing utensil for this lab. If you don't have one, please do go and get it or get something. As I start in here, feel free to go and grab that. Just good to have something to write with and something to write on. Okay, so let's get started. So a little review of what we saw last week and a little more this week. We can represent quantum states using a vector. For us, we generally say that this vector is basically two numbers that we've packaged together like this, where the top number represents the component of 0 that our state is. So our state has some amount of 0 and some amount of 1. The top represents the component that's 0, and the bottom represents the part that's 1. These vectors that represent quantum systems are called state vectors because they represent a quantum state. So any vectors that represent a quantum system or a quantum state are called state vectors. they must be normalized to 1, as in their length or their norm must equal 1. Okay, so it must equal 1 because fundamentally the length is the total probability of measuring something, of getting one state out when you measure. Okay, and you have to get some state out, and it also doesn't make sense for there to be a 200% chance that you measure a state out. You need a 100% chance that you get it out. And so while there are many vectors, technically an infinite number, there are fewer state vectors. It's a restricted thing. State vectors are a very special kind of vectors. State vectors have a length of 1. And to find the length, you do this. For a vector with A on top and B on bottom, you plug it into this formula, which if you've seen the Pythagorean theorem, that is exactly what this is. So that's the way I typically think about it. If you had a triangle with legs of A and B, you find the hypotenuse like this. If you don't like that, if geometry is not your thing, that's totally fine, but we really can interpret it this way. But basically, it's square root of the first number squared plus the second number squared. That's how we get the length of it. How we take these two numbers that have been packaged together and say, what is the total number representing the length? If this length, this square root of A squared plus B squared is 1, we call the vector normalized. That means it is a state vector. If the length is not 1, we use this equation to normalize it. Basically, we divide by that number. So if you got out a length of 2, well, you just say, let me just have it, right? Let me have it here. So 1 divided by 2 here. Okay. Gates, and this is a new part from when we discussed last week, gates are represented mathematically as a matrix. So a matrix looks like this down below. It's a lot like a vector, but it has two parts to it. It has not just a column, it also has rows. So you get a 2D grid of numbers, basically. We multiply a matrix by a quantum state to find our new transformed quantum state. So basically what you do is you take a gate, you multiply it by a quantum state, and you get a new quantum state, right? We've seen that with applying, say, an X gate to the 0 state, and you get 1 out. Well, we can represent that mathematically as the matrix times the vector, getting us a new vector, a new state vector in particular. So as an example here, we have this mystery matrix, let's say, and we multiply it by the vector that this block sphere represents, which would be a 1 up top and a 0 down below. And then we get this out with a 0 up top and a 1 down below. This is in fact the X gate. This is how we mathematically represent the X gate, but we don't have to focus on that in particular. It's just an example. The idea is a matrix times a vector gets us a new vector. So we can basically apply this formula. The matrix, which is a gate, multiplies by a vector, which is our old quantum state, and out we get a new vector that's the new quantum state. So let's practice. Really, this stuff makes the most sense once you start seeing examples and practicing. So the first math skill we need to focus on is finding the norm of vectors. So this is the summary in general. Again, the norm of a vector is a fancy word for the length of a vector. We use the norm to normalize a vector representing a quantum state. Again, if a vector is not normalized, we just divide by this number to make it normalized, right? As is pointed out here. So what I'd like to do is give you all some time to work on this. I'll give you a couple minutes to work on these examples. Don't worry if you don't get through all 3, particularly if this is very new for you, that's totally fine. Just focus on this first one. And if you happen to finish it up before we start discussing, then move on to the others. So I'll give everyone a few moments to work on this. And if you haven't already gotten a paper and pen or something to write with, then now is a great time to do that. So, all right, I'll give you all a moment. Here's the previous slide pointing out normalization. And here's our examples. If everyone could just give me a thumbs up when you're done with the first example, or give me a thumbs up if you're feeling like I just have no idea how to do this. So either way, basically, if you've done everything you can on the first example here, go ahead and give me a thumbs up whenever that happens.
All right, folks. So let's get started on this then. So take a moment to pause and we will walk through this example together, this first example. So let me switch to the annotation and then we can walk through it. But I am curious in the meantime, if people would like to provide their answer. What is the norm of that first vector? You can go ahead and provide it in the chat. What's the norm of the first vector? Okay, seeing some ones. Yeah. Okay. Yeah, I agree. It's 1. So let's see how we get that. So we want to find the norm of this vector here. So what we do is we say 1 over the square root of 2, all squared. And then we add that again. Just like this, all squared, and then the whole thing square rooted. So it's a little bit to set up, but basically it looks like this. This is the standard formula for finding the norm. We take the first number here and we square it. We add the second number and square it, and then we square root the whole thing. So then we can simplify that to, well, the square root is going to stay for now. We have other steps to deal with first, so we just keep it along for the ride for now. 1 over square root of 2 squared can seem a little complicated, but a square always undoes a square root, right? They undo each other. They're the inverse technically. So this is 1/2 plus 1/2. Now, the point of this is for you to understand the general formula and how to apply it. It is not for you to be very quick at math. So you are totally fine to use a calculator. If you want to use a calculator here, that is completely fine. That is not the point of this. If you like to kind of, keep yourself fresh with this and try it out on your own without a calculator, great. But for the sake of understanding, that's not the focus today. The focus is under understanding how to apply the formula, not how to actually calculate these numbers. So basically you'd enter 1 over the square root of 2 and then square it on your calculator and add it to the same thing. Well, 1/2 plus 1/2 is 1. So we square root that, and that is in fact 1. So I agree. It is 1. So now I want to hear from folks. Is this vector normalized? So we just found the norm. Is it normalized? Yeah, awesome. It is. This is a normalized vector. When we get 1 out as the norm, that is the definition of a normalized vector. So this is in fact a normalized vector. It corresponds to some physical real state. Awesome. Okay, I'm going to go through the second example now. If you did it, great, follow along, see if you and check your work. If not, then feel free to follow along and try it yourself. We'll also have some more examples for you to work on after this. So notice that we now have 3 elements. So this might look a little funny, right? Yes, so the norm of a vector is its length. So these are 2 different words for the same thing, just to keep you on your toes. So now we have 3 elements, and we want to find the norm or the length of this vector. It's the same idea. You take the first element and square it, plus the second element and square it. And now we take the third element and square it. And then square root the whole thing. The same general formula, but we just add the square of every single number we have. So then this becomes 1 plus 1, right? The square of -1 is just 1 plus 0. I'm just keeping it along there just to be very clear about what's happening. Then that's 2, like this. So we get the square root of 2. I'm not going to simplify it anymore because it doesn't look very nice after that. It's in fact known as an irrational number. But the important question is this a normalized vector? We just found the length or the norm. Again, those are 2 words for the same thing, length and norm. We just found the length to be square root of 2. Is this vector normalized? Okay. Yeah, I'm seeing some people picking up on the fact that this is not normalized. Square root of 2 is not 1, right? You can kind of imagine square root of 1 is 1. So anything square root of larger is going to be larger than 1. So in fact, it isn't. Can anyone tell me, what do we have to do to normalize this vector? If I say I want to have a normalized real physical state vector, what would I have to do to this to normalize it? And try to be as specific as possible to this case. This specific vector, how do I normalize it? Yeah, I've got to divide by root 1 by root 2. So specifically what I do is, and actually I'll try to make it a little clearer than even that. I'll say we have 1 over the square root of 2, that single number, and we multiply it by the vector. Note that that's the same as if I said the square root of 1 over the square root of 2 up here, -1 over square root of 2 here. Multiplying by a number out front of a vector is the same as multiplying by each of the elements. Okay, awesome. Great. All right, then the third example. So again, running through this, we get the square root of 2 squared plus -1 squared. Try not to run out of room. Plus -1 all squared. And again, pardon for my drawing. And then we get 2 plus 1 plus 1, and we square root the whole thing. That is in fact the square root of 4, which comes out to be 2. This is very much not 1. So it is not normalized. And to normalize it, we divide by 2. That's a big one. 1/2 of this vector would be normalized. Any questions on this slide here? Any questions on these examples? Generally, how are we feeling right now? Let's say I want to do a little check-in. Scale of 1 through 5, let's say, 1 being totally lost and 5 being great. We can keep going, don't even need to do any more. Where are we at? And anywhere is fine. I just want to make sure that we're focusing on the key skills for you all today. Pi, it's a nice answer. Another irrational number. Okay. Okay. What I want to do is I want to make sure that we have time to look at some of the newer parts as well. We are going to keep practicing all this, so even if it's not crystal clear, that's fine. But let's go ahead and look. We can come back to this later. Okay, and just to answer the question there, Amar, norm, length, and magnitude for us are all going to be the same thing. What a wonderful world we live in, that we have 3 different terms for a confusing concept. Okay, so we talked about normalization. It has to have a length of 1. We have this new concept, though, called orthogonality. Orthogonality, it's quite a word. It takes a while to get used to saying. But when we are multiplying 2 vectors together and it yields a 0, we call them orthogonal. So for example, 0 and 1 are considered orthogonal. So we can see this, and I'll show you quickly here. If we take 1 and 0 and we multiply it by 0 and 1, to follow along, how we do this is we take, let me see, try to find a decent color here. We take the 0 and the 1, or sorry, the 1 and the 0, and we multiply them together. So 1 times 0, hopefully this isn't too light for you all. And then we add the result of the same thing down here. So 0 times 1, which is then 0. Big fat 0. So in fact, the result of multiplying these together is 0. Now, multiplying vectors may be a new skill as well. It likely is. And so I'm not expecting that to be totally crystal clear. But the point is, you multiply the elements at the same part. Basically, you say, by multiplying these 2 vectors, what I'm doing is I'm multiplying the components that are 0 and the components that are 1. So in other words, we're saying that when we look at the joint combination of zeros, how much 0 we have here, 0 state, and how much 0 state we have in this vector, they are completely different. Right? This one is 100% 0, and this one is 0% 0. So of course, the contribution from 0 is 0. There's no overlap here. And then the same thing for the bottom. So when we multiply vectors like this, what we're doing in some sense is finding the overlap of them. How much are they alike? How similar are they? When you get a 0, we're saying they are not alike at all. They're 0% similar. So in some sense, we say they are total opposites of each other. They are orthogonal. And yeah, there's some nice ways to do this using NumPy for those familiar. Thank you, Wayne. So let me clear the text here. So you may be thinking about 90-degree angles. It's okay if you're not. But orthogonal actually relates to 90-degree angles. That's another way to say it. So basically, when you have the, get rid of the annotations here. When you have 2 parts here, 2 vectors, and they are 90 degrees apart, then we say they're orthogonal. So orthogonality becomes really important because of this idea of measurement bases. It's what makes 0 and 1 total opposites of each other. That's why they sit on opposite sides of the Bloch sphere, as opposed to, say, 0 and the plus state sitting much closer to each other. Now, it is important to point out, and this was commented last week as well, the Bloch sphere can be a little misleading because we have different angles than other places. So do be careful of that. So think of the Bloch sphere in terms of the qualitative amount, how opposite are they, but do not think about degrees. Really here, we're thinking about degrees of one vector being 90 degrees to another vector. In other words, if you were to head along those vectors, you would go off in completely opposite directions over time, right? Imagine the opposite case of instead of 90 degrees, you're 0, you're gonna head in the exact same direction the whole time. or at least a similar direction. Okay, that orthogonality point is one that we'll come to with time. It's a nuanced point. From the previous section, the key part to me is that you know how to normalize a vector. If you know how to normalize a vector, you got what you needed from that last part. Now let's look at matrix multiplication. So you have a matrix times your initial state and you get your final state out. So this is how we do it. First, if we have this matrix here and this vector here, we multiply the first number in the first row of the matrix with the first number in the initial state. In other words, 0 times 1. We take this 0 and this 1, and we multiply them. And then we add the second number in the first row with the second number in the initial state, 1 times 0 here. So this 1 times this 0. In some sense, you kind of push this vector onto here. So you push the 1 onto the 0 and the 0 onto the 1, and that gets you the top row. Then we do the same thing for below, where now we go to the next row. So we say now we're going to multiply this 1 times this 1. So the first element of the bottom row with this first element of the vector, and the second element of the bottom row with the second element of the vector. And we get this result F. Now, this is a complicated process, particularly if you haven't seen it before. So I do want to stop and see if there's any questions right now. We'll see some practice for sure, but how are we feeling about this? Do we have any questions at the moment? Okay, let's keep moving. So let's do this together first, and then we'll go through some examples that you can work on yourself. So let's start with this. So if I'm given this matrix and this vector, and note we're not worrying about normalization or anything like that here. We're just doing linear algebra generally. As you get more comfortable with all of this, you'll start to quickly recognize that, for instance, this is not a normalized vector, things like that, but it doesn't matter here. The rules are the same. So what we do is first, I say, okay, I'm going to compute the top part, right? So I take 1 times 1. That's this part and this part. And then I take, let's say, this part and this part and do plus 1 times 1. And that gets me the top row. Then I can do the same for the bottom. -1 times 1. And then a nice 3 times 1. So plus 3. I'm going to fix that up a little bit at least. Plus 3 times 1. Awesome. Okay. So that's how you set up your matrix. And we'll simplify this in a bit, but the really, really important part, because again, you can enter this in a calculator, that's fine. The important part is setting up these calculations. So seeing how these numbers match, right? So the first row of the matrix goes to the first row of your first, the first row of the new vector, or the first part. The bottom part, the second row, goes down below, right? That's the general idea. And in both cases, you're taking both parts of the state. Now, what that equals in the end, in this particular case, would be 1 plus 1, which is 2, and then -1 plus 3, which is in fact 2. So this is the vector 2, 2. Any questions on that so far? Okay, then let's go ahead and work on the matrices now. Yes, you may have noticed that that state was a little suggestive. 2 is an unnormalized version of the plus state. We will get into those kind of things as we go, but yeah, nice eye, nice catch, Amar. Okay, now multiplying two matrices is actually very similar. We basically treat it as though they're two different vectors. So we go like this, and we say, okay, we take 0 times -3. And then we add 1 times 2 plus 1 times 2. And that gets us this piece. And then we can do the same thing down below. Again, right now I'm almost pretending this second part of the matrix doesn't exist, and I'm imagining this just as a single vector. So it's the same exact thing as if you just had a vector here and we ignored this other part, right? So you can almost imagine maybe doing something like this for the moment, right? Just doing that for the moment. And in this case, it's identical to what we had before. So now we do the -1 times the -3. So -1 times -3, and then plus -1 times 2. Oop, that's pretty messy. Okay. Then we now have to deal with this second part that we just kind of had. So what I would say is, now we just pretend that we have a new vector here. And we do the same thing again. So 0 times, there it is, times -1. So we're over here, and I'm going to really emphasize this is not added on. This is an entirely different part, right? We're going to get a matrix out. And then plus 1 times -1. And then repeating the same thing for the bottom, and then we're almost done. -1 times -1. And last but not least, another -1 times -1. Okay. And in the end, we have our full vector here. Or sorry, matrix here. So we can simplify this a little further, but again, that is not the main focus. The main focus is just on you being able to set up these things. However, just to see it in the end, simplified, 0 times -3, 0. So we get 2 up here. However, whatever order you want to do this in. This is 3 minus 2, 1. This is -1. And that's 1 plus 1, so that's 2. So in fact, we get this matrix out, this matrix out. That's just simplifying the math from above, which again, you are free to use a calculator for. Okay, a little more complicated, but again, the method that makes sense to me is get down how to multiply a matrix with a vector, and then just pretend that each part of your second matrix is its own vector. And basically you're just stacking them along here. There's actually some deep math saying that that's an acceptable way to interpret it. We don't have to worry about that deep math, but just know that that's not just a trick. That is actually a valid interpretation of what we're doing. So you can take each part of this and multiply it by each part of this. So we go rows and then columns. Okay. And yes, to answer some questions I'm noticing, when you have a gate times a state, you will always get a state out. So it'll always be a column vector, really, a column vector. So a gate times a state like we had previously, right? Like in this, let me get rid of that. Like in this example, you always get a column out of one single vector. So if you start with a vector and multiply by a matrix, you get a vector out. If you start with with two matrices, you'll get another matrix out. Always the same, and it always follows the same pattern. Okay, now I'm going to give you this kind of complicated one. This is a little trickier, but just try to follow the same logic as we've used. I'm going to go ahead and give you a couple minutes to work on this one. So go ahead and work on this. Multiply the following vector with the following matrix. And let me know if you have questions.
I guess you are muted.
Thank you for pointing that out. I was just going on a whole discussion there of norms of matrices. Yeah, it's a great question to ask about the norms of matrices. Once you start getting familiar with the mechanics here, how you do these things, which is the most important part, it's worthwhile to start wondering these things. Like what does it look like in these other cases, right? We talked about norm of vectors. So there is such a thing as a norm of a matrix, or there are actually several different ways to talk about it. It is a little important, but there's so many different ways to do it that we kind of have different reasons for using different ones. And it is related to this idea of unitary matrices, but it's also just one part of it. But yeah, great question to ask. All right. Seeing some folks pass along some answers, so I'll probably hop in a minute. I'll just give folks a second to start wrapping up. All right, so let me get my annotation tools out. Okay, great. That's a great question, Alessio. Yeah, so notice that we've kind of been jumping around between vectors with 2 or 3 digits here. Technically, this would describe some other system with 3 possible states. We don't have to worry about what that means physically, but technically you can have something called a Q trit instead of a Q bit, and that would have 3 states. These are physical systems. These are things you can do. You could even form a quantum computer using them. But for right now, we're really just trying to focus on the math of it. So honestly, this vector is not normalized. It's not a physical thing. My guess is that this matrix doesn't correspond to a real gate. So just worry about, or just focus on the math, but it's a great question to be asking. Technically, we can have vectors of any size, and so long as they're normalized, they represent some sort of physical state out there in the world. Okay, so it's gonna be a little complicated, but let's see. I'll just go a little faster than before. We'll say 2 times 1 is 2 plus -1 times 1 is -1. And then we get a plus 0 here. So keep in mind, we have 3 numbers, but we just do them all together here in one place. And then we get 2 times 2 is 4 plus 0 times 1 is 0 plus 1 times 0 is 0. And then 1 times 2 is 2 and then 2 times 1 is 2, and then we get another 0. Notice that this 0 is just kind of canceling a lot of things out. And then we have we go further down. So now we go with 2 times 2. Let's see, where are we? 2 times 1 plus minus 1. So that'll end up equaling out. Oh, sorry. Yeah. So that'll end up equaling out our, let's see, 1, 4, 4. I believe that matches what folks got. 1, 4, 4. Beautiful. So I know I walked through that quickly. Please do let me know if you have questions. But generally, this is the idea. One thing I want to point out that's related to a question someone had asked is that if you notice here, we started with a vector that looked like this. It had 3 digits, and maybe it didn't seem as comfortable or familiar as before, but basically we started with this. So long as we multiply by a matrix that's a square like this, that so long as we multiply by a matrix, anyone that we're going to see, you'll always get something out of the same shape. So when you multiply a matrix times something else, you'll get the same shape as that something else. Even if this is another matrix, you'll just get another matrix of the same size out. So one thing I would encourage you to do, even if you're still getting this process down, is before you even start going into the math, just look at this and think, okay, what should I expect to get out here? Well, in this case, we have this kind of vector, 3 numbers, what's known as a column vector, 3 numbers in a column like this. So we should expect 3 numbers in a column like that. So it's a good thing to just kind of check before you go into it and then after, right? If you get a matrix out of this, something went wrong. And you know that because you'd say, well, I just multiplied a matrix times a vector. I need to get a vector of the same format. Okay, any questions on that? Okay, awesome. So now we multiply the following matrix with the following matrix. I will give everyone a moment or two to work on this. And this is one of the last things we'll be doing today. We'll also talk a little bit about what this physically means, but go ahead and work on this and let me know if you have questions. Yeah, go ahead and pass along your answers as you get them. Share with each other. Okay, I appreciate folks sharing, and yeah, Umar, it's it's just to be expected. Even once you get comfortable with these things, it's definitely easy to make mistakes. But it looks like you got there in the end. I agree. It does in fact come out to be that last one that you said. Walking through this, first of all, if we have a 2 by 2 matrix like this, as in like 2 numbers up top, 2 numbers down below, or 2 rows, 2 columns, however you want to think of it, basically whatever shape we get in this kind of matrix, we should expect that out. So basically we should expect to be calculating 4 different numbers and to get a shape like this. Unlike in the previous example where we had a vector going in, so we should expect a vector out. Again, it's a good first check before you go charging into the math to just think, what should I expect to get out of this? Okay, so we take -1 times 1, -1, and then we add 0 to it, 2 times 0. Then we go -1 times 2 is -2, and again, plus 0. Then we look here. So again, I've kind of looked at this as one vector, and then now I'm looking at this as another vector. So we go 1 times 1 plus 2 times 2, and then 1 times 2 minus 2, because it is -1 times 2. And so we in fact get out -1, -2. Sorry, I think I did. No, yeah, okay. And then we get out 3 and 0, I believe. Okay. Now do check my math. Again, we all make mistakes. Do we agree with that? Does that make sense? I noticed a few different answers out there, so do check. It's very possible I'll make a mistake, but generally it should look like this. Yes, I did make a mistake. I was looking for where that was, specifically up here. So notice that I said 1 times 1, and then I got a little sloppy there, a little overconfident, and I just did 1 times 2 here. But in fact, this should be 2 times 2 over here, so that's 4. And then that means this comes out to be 5. Okay. So in fact, this is the correct answer. Okay. Awesome. So let's continue on. So I want to talk a little bit about the physical ideas here, why we're even learning this in the first place, just in the last few minutes here. So again, gates are represented by matrices. So these grids of numbers are a way to talk about gates, and vectors are a way to talk about quantum states. Here are specific examples, as you saw in lecture. So the X gate looks like this, the Z gate looks like this, and the H gate looks like that. It is always the same thing. Just as there is one vector representing the 0 state, there is one matrix representing the X gate. And these are the primary ones. You will end up seeing, as you dig into this more, this idea that there's kind of vectors in here, hidden in here, but I wouldn't worry about it too much for right now. So when we say that we're applying an X gate to the 0 state, we're saying we're applying this matrix times the 0 state. Does anyone happen to remember in the last few moments here, what does the 0 state look like in vector form? How do I write a 0 state in vector form? Feel free to send it in the chat or speak up. What is the 0 state? Do you remember? Yeah, awesome. It's a 1 up top. Awesome seeing it from folks. Awesome. Like this, 1, 0. That's the 0 state. So what we've written up top here is the same as what we've written down below. So then when we multiply this, we say 1 times 0, which is 0, plus 0 times 1, which is 0. Then 1 times 1, which is 1, and 0 times 0 is 0. And so we get out 0, 1. Can anyone tell me what is that state? This is now a little trickier. We're going from a vector to a state. What is it? What state does this represent? Yeah, this is the 1 state. So whether we look at it as gates and kets, or we were looking at rotations of the block sphere, or we're looking at the math, they should all agree with each other. This is how the X gate works. And in fact, this is how you can figure out what the form of the X gate matrix is. For those of you that are feeling a little more advanced and things like that, I've seen this before. I'd encourage you to, in fact, see if you can figure out why the X gate looks like this by basically plugging in variables and making sure that they work so that this comes out to be the case. You can, in fact, solve for them based on what they do. For those that are feeling like this is brand new and we're just getting comfortable, don't worry about that. The interesting thing is to notice that we get the same result out, whether we're looking at kets, 0 and 1, and our X gate, or matrices and vectors. Okay. Now we're approaching the end here. So, and I'm glad we got to that point here. This is something we will see as we go. You could do something similar with the Z gate and the plus state, or the X gate applied to the 1 state, and so on and so forth. Again, we will not be going into those too much, but this is the main point that I wanted to go through today. There's also the Qiskit notebook, which I encourage you to go through if you have time this week, just to keep fresh on those things. All right. So we've seen everything that I wanted to go through today, in particular, looking at the norm of matrix or vectors. How do we calculate the norm of a vector? And then how do we normalize a vector? And then how do we multiply matrices times vectors and other matrices? This is a lot of math. We're in the course of 2 weeks, you're basically taking a crash course in linear algebra. So that is a lot. So please, if you're feeling overwhelmed or anything, reach out to me, to other groups, go to talk with each other, keep practicing things. Anything that you find helpful, definitely let us know. And otherwise, just keep practicing, and I'll see you next week. Have a wonderful week, everybody.
See ya.